Idea then we'll talk about is the activity series. Now the activity series is a list of metals arranged in decreasing ease of oxidation. This may sound a bit complex, but we'll show you some examples and it'll make a little more sense. Here it says the higher the metal on the activity series, the more active that metal is, and that's why it's called the activity series. A metal above will replace a metal below in a single replacement reaction. From the perspective of oxidation reduction, we can say that any metal can be oxidized by the ions of elements below it. Okay, after we do some example problems, you can go back and this will probably make a little more sense. The nice thing, you actually don't have to memorize the activity series. It'll be given to you, but you should know the general order of the elements in the activity series. Alright, so here is the activity series. Now at the top, we have listed the most active metals. Metals like lithium, potassium, barium, sodium. These are the group 1 and 2 metal ions. Now we know that group 1 on the periodic table is very reactive. The alkali and alkaline earth elements, these right here, are very reactive. At the very bottom, you got things like, you got the noble metals, or the least reactive metals, gold, platinum, mercury, silver. We know that these elements were the noble metals. They sit in the bottom. And right in the middle, right here, you have zinc, chromium, iron, cobalt. You actually have your standard D block elements. So this is the general layout of the activity series. Now, the higher the metal, the more active the metal. So the more active the metal, the more likely it is to be oxidized. So if potassium is really active, it will not exist as potassium in a reaction. It'll exist as potassium plus. An example of gold, gold actually will exist. Gold is not active, so it will not exist as a plus, as a positive charge. It'll exist more as a neutral atom. And that's really how this activity series works. It's very logical. It just says that iron is more likely to react than platinum, which everybody knows is the case. Iron rusts much more easily than platinum does. Platinum actually does not corrode. You can have platinum sit in water for a while and it'll remain platinum. But we know, say iron versus barium, barium is much more reactive, so barium will corrode much more quickly in air than will iron. This is just that logic placed out in the activity series. Okay? So we can ask a question like this. Which of the following metals will be oxidized by lead nitrate? So when lead nitrate reacts with any of these three, the one that's higher on the activity series will essentially replace the lead. So the activity series asks, can zinc replace lead? That's what the activity series asks. If zinc is higher up on the activity series, so since zinc is up here and lead is down here, and that is the case, zinc is higher up, then zinc will be able to replace lead. Now when zinc replaces lead, zinc then is oxidized, because whichever element is in a compound, that's the element that has a charge of +2. In this case +2 because you have two nitrates balancing it. So when zinc replaces lead, it becomes a +2 charge. And you get yourself zinc nitrate, which means zinc has been oxidized. So this is a fancy way of asking who is higher on the activity series, and that's it. Now, if we analyze copper and iron, take a look at the activity series. So here is iron on the activity series, here is copper, and here is lead. What you'll see, so previously we saw that zinc was definitely above lead. Now we see that iron is above lead, but copper is below lead. So copper will not be able to replace lead, in other words. Whoever's more active gets to replace the other element. Whoever is more active gets to remain +2 or +3, whatever it is. Whoever's less active gets to remain 0, neutral. So in the case of this reaction, lead can be replaced by iron, but not by copper. So iron can come in here and replace lead, but copper cannot. And that's the idea. So hopefully this makes sense. So in this case, the answers are zinc and iron. Alright, let's go ahead and do a few reactions using the activity series, and then this will complete the lesson for us. So we'll use the activity series to now predict whether these reactions will take place. And that's the power of the activity series. So the question here is, can calcium replace potassium? Usually we show these reactions simply as a single replacement reaction, and we say, yes, this happens. But now we have predictive power. We have to ask ourselves, is calcium higher up than potassium on the activity series? Looking at the activity series, calcium is actually below potassium. So calcium will not be able to replace potassium. Calcium will remain zero, potassium will remain a positive, because the higher the metal, the more likely it'll become a positive. So potassium will not be able to be replaced by calcium. So in this case, you actually have yourself no reaction. So the activity series predicted that this reaction will not happen. How about magnesium versus zinc? You're asking the same question. Can magnesium replace the zinc? Well, is magnesium higher up than zinc? Yes, it is. Check the activity series. You'll see that magnesium is more active than zinc, which means this reaction will take place. Magnesium will react with zinc. So we can actually put magnesium chloride and zinc. And then the equation should be balanced as it is. Remember that magnesium has a +2 charge. That's why it has to be MgCl2. Now in this case, we don't worry about net ionic equations. Eventually, if we had to write a net ionic equation, it would actually look like this. I can show you real quick for that purpose, since we just talked about zinc has a +2 charge. In this case, chlorine will actually be the spectator ion. Magnesium has a 0 charge. That's what you begin the reaction as. And then afterwards, you get magnesium have a +2 charge and zinc be neutral. What you see is you see zinc being reduced, you see magnesium being oxidized. That's because magnesium is more active. The more active you are, the more likely you are to be a +2 charge. So this is the net ionic equation. We're not asking for it here, but I thought to show you so you can see what's happening. Iron sulfate C versus cobalt. All right, we have to consult the activity series. Now sometimes with the previous example, I can guess that magnesium is more active than zinc because magnesium is in the S block and then zinc is in the D block. But here I have both iron and cobalt in the D block, so we have to consult the activity series. We probably couldn't predict. Activity series is getting pretty messy. Let's see if we can clear it up a bit. Maybe. Alright, so we get iron versus cobalt. Looks like iron and cobalt are right next to each other. Iron is a little more active than cobalt. So, cobalt being less active, looks like the rest of this is erased. Cobalt being less active will not be able to replace iron. So cobalt cannot replace iron. In this case, we also have no reaction. Alright, and then our final equation is KBr plus chlorine gas. Now, in this case, we have a nonmetal trying to replace, this is chlorine, an element in a compound. And remember that the nonmetal will try to replace the nonmetal. Chlorine will actually try to replace bromine. So we need an activity series with chlorine and bromine. But it turns out the activity series we gave you were only for metals. Well, let me give you another activity series. I will give you the nonmetal activity series. And the nice thing is, this activity series is really simple, and it's essentially for the halogens. And the activity series is actually the order in which they appear on the periodic table. So it's simply fluorine, chlorine, bromine, iodine, and then astatine. So astatine usually is rare, radioactive, nobody messes with it. So it's really these first four. So the more active metals, now we knew that, or sorry, nonmetals, we knew this because we know that reactivity increases going up a group. So we know fluorine is the most reactive element. So chlorine is more reactive than bromine, which means chlorine can replace bromine. So this reaction will happen. And you get yourself KCl, and then you get yourself bromine by itself. Remember, bromine is diatomic. You get KCl plus Br2. So this reaction does happen, and the activity series is simply the activity of the elements from the periodic table. Okay, so also know the nonmetal activity series, but as in this example, it's pretty simple, and I will have you remember it. Let's go ahead and remember this one. Okay, hopefully that made sense. Try this example problem on your own, and this completes the lesson.